core. Okay, very good. So we did this. Last thing we did, I guess, was what? Was it Hodge decomposition? I guess we did Hodge decomposition. So to do some examples of that, to give some examples, I think I want to review quickly this Hodge star operator, if you don't mind. I'll just quickly review Hodge star. We had a quick review, but it was not very. It was so quick. So a review of Hodge star operator. So what's the point? So the point is that imagine you have a finite dimensional vector space, say over R, over R, and imagine it's like its dimension is like n. Then we know that wedge P of V and wedge n minus P of V have the same dimension. Then dimension of wedge P of V is equal to dimension of wedge n minus P of V, which we know, of course, is equal to n choose P, because this is equal to, I mean, the reason for this is that n choose P is equal to n choose n minus P. Right? This being dimension of that, and this is dimension of that. So the duality in Pascal triangle, or binomial coefficients, duality in binomial coefficients gives us this isomorphism. I mean, okay, so this equality of dimensions, but the point is that there is no natural map from wedge P to wedge n minus P. I mean, I don't know how to prove this, but I just make the claim no matter what. No natural map. Well, I mean, you have to also work, what does it mean to say no natural map? So you have to think. So this is some statement that I don't elaborate more, and I don't try to prove something that I haven't even elaborated exactly. So but it's something good to think about for yourself. But I say no natural map, or in fact isomorphism, from wedge P V to wedge n minus P of V. So I should say but. So these two vector spaces, of course, because their dimensions are the same, they are isomorphic, but the isomorphism is totally unnatural. You can just say any isomorphism, the dimensions are the same. Natural. So to get natural isomorphism, get a natural, I would say maybe canonical isomorphism. We can proceed like this. We can equip V with an inner product, put a positive definite inner product. So let's denote it like this on V. Then we also choose an orientation for V plus an orientation V. So we need these two extra pieces of data. We need some Euclidean structure, which is positive definite inner product, and an orientation on V. Then I claim that there exists indeed an isomorphism, canonical isomorphism, which would depend on choice of inner product and on choice of orientation from wedge P to wedge n minus P. And that's what Hodge star operator does for us. So to get star from which P of V to wedge n minus P of V. So this is this Hodge star operator. Okay. So that's the idea. That's what we want to do. Let's see how this can be done. So first of all, we can use these two structures, inner product and orientation. We can define an element. I call it d volume. Maybe it's not very good, but I just put it. Let d volume, by definition, be equal to E1 wedge n for any oriented orthonormal basis. For any oriented orthonormal basis of V. So I guess you can see it there. So this element now belongs to, of course, wedge n of V. So it's a top exterior element in wedge n of V. Now, of course, the first thing you have to check is that this is independent of choice of oriented orthonormal basis. So check that. These are some little exercises you have to do. Check that the volume is well defined. That. So okay. So once you have that, then you can prove this lemma. So then we can exercise. The exercise is this. There exists a unique linear map. Unique linear map star. So I should say for any P in this range, there exists a unique linear map star from wedge P of V to wedge n minus P of V, such that inner product of star of omega and eta is equal to times d volume is equal to omega wedge eta. So we use the wedge product in combination with this inner product and d volume to get this definition for star. So this is now for any omega belonging to wedge P of V, and for any eta belonging to wedge n minus P of V. So when you multiply these two things on the right-hand side, you get something in wedge n, you get the top form. And here is a number, and this is your top form over there. Now, this is an exercise like this one, but to check this, you just use the fact that the linear transformation on a vector space, on an inner product space, is given by inner product with respect to a vector. So you're looking for this vector, star of omega, this mysterious vector, star of omega. But this vector is defined in such a way that its inner product with any other vector is going to be. So you can just take this as your maybe linear transformation. I mean, this divided by this d volume essentially as your linear operator on omega on wedge n minus p, and then you know that such a thing exists on wedge. So anyhow, so that's the idea. The idea is like Riesz representation theorem for inner products and linear transformations. Okay, so this exists. That's and this is and is an isomorphism. We'll see soon why this is an isomorphism. What properties? So this is a very nice way to implement this map that we desire to have, like that, and that's Hodge star. So Hodge star by itself is something completely linear algebra. It's complete linear algebra, but it's beautiful linear algebra, of course. So now, examples of this, of course, for example, star of say 1, that's equal to E1 wedge En. So that's going to be equal to 0. And star of E1 wedge En is equal to 1. So this is going to be equal to N. And in general, you can say star of EI1 EIP in any order. I'm not choosing any increasing or decreasing order in any particular order. It's a star of this guy is equal to epsilon. Okay, epsilon times EIP plus 1, which EI. So this demanded. Epsilon is the sign of a permutation which is sending 1 to N to I1, I2 to I. So because we have written these guys in some order now, right? Like that. So the sign of this permutation is going to give us this correct factor so that the equality. This also you can check. I mean, so I'm giving all these things. So this EX could be an exercise or example. So it stands for both. You're helping yourself. Okay, so also check that, these are nice exercises. Check that the star composed with the star is equal to -1 to the power n times n minus p. So this, of course, goes from HP now to itself, right? Because one star goes from HP to wedge n minus p, and then you do the duality, you come back to HP. So that's okay. Any questions about this star operation? Okay, so this is good. Now, one thing that's important to know is that how can you write this volume form or volume element or this top form here in terms of a non-orthonormal basis? So imagine there is some general basis. We need to know that. So here is another nice exercise. This form the volume. So this is exercise. I highly recommend this. Is that for any oriented basis, F1, F2, N of V. So this basis now need not be orthonormal. It's just it could be any basis, but oriented. So I just say need not be orthonormal. Orthogonal or whatever. So what happens is that this D volume, which we define to be E1 wedge N, right? So this is equal to square root of determinant of G times F1 wedge F. So when you do F1 wedge Fn, you get another element in the top exterior power, but that's not the volume form. It has to be corrected by this amount. What is G? So G is equal to Gij is equal to Gij inverse. But now this Gij, this Gij, so I can just say, for example, Gij is in the inner product of Fi star and Fj star. The dual basis for that. Okay. So this Fi is the dual basis. Fi star Ej is equal to delta J. So it's for that, of course, Gij is equal to inner product of Fi and Fj. Again, you can define it this way, or you can define it by the inverse, and the result is that actually they are the same. But define it like that. And this is Fi, Fj. This is just in the chosen basis. This is the metric in the chosen basis, right? So
you mean Fi star Fj is direct.
For which one?
Fi star Fj is direct.
This one?
Yeah.
Oh, Fj. That's the duality. Yeah, exactly. Okay, so this is also a very important proposition. Part of the exercise I want you to do. So you have to. Okay, so that's nice. Now, okay, I believe that's all linear algebra for now that we need. Now we go over a manifold to implement these ideas. Okay, so now we can assume now M is a. So now let Mg be kind of oriented Riemannian manifold. So I'm just assuming that it's an oriented Riemannian manifold. So now we can define this star operator on forms, right? Just point-wise, and define star from omega p of m to omega n minus p of m. I mean, why is that? I mean, the reason for this, of course, is that this is nothing but the infinity of wedge p of t star of m, right? So, I mean, if you look at fiber at each point, you have wedge p star at x m. So you can use your orientation and your metric to define an orientation and metric on each tangent space and on the cotangent space as well. So then you use this formula, so you define point. So this operation is completely algebraic. It's nothing to do with differentiation. You're not differentiating when you're applying this stuff. It's pure algebra because everything you did is just pure algebra. Okay, so we have that. That's Hodge star. And the volume form in this case, using this result, the volume form is the famous volume form of Riemannian manifolds. And U is equal to square root of determinant of G. This is dx1, which dx2. You see, this is now a non-orthonormal, non-orthogonal basis for the cotangent space at each point. So I can apply this result to this, and that's what I get here, because my metric G is originally not defined on the cotangent space, it's defined on the tangent space. So, but the dual of the cotangent space is the tangent space. So when you use this result, you can get this. Well, this is like, so that's G, really that Gij equal to that of this inner product of ddxi, ddxj, right? That's the definition of this Riemannian matrix in that coordinate system. Question? There is some duality, some extra duality going on. I'm just using it, but it's clear.
So on the right of the board, we have that we have described that G. There, G is the
on the dual space.
Yeah.
The metric on the dual space.
Of course, yes.
But here we are on the dual space, so on the dual of the dual on the tangent space. So there is some confusing duality going on, different dualities going on. Okay, so this is it. That's it, and then. So using this stuff now, we can define an inner product. Inner product on omega p of m. So notation I use is like this curly bracket omega prime. So this is going to be a number. This is going to be a number. This is equal to integral. So what I'll do, point-wise, I'll just take the inner products, right? And then so this is a function, and then I integrate it against this volume form over there. Or sometimes people just write d vol G, but just write d vol. Right? So this integration is over. Huh? Of course, I mean, if M is compact, then you're okay. If not, you just restrict to compact support form. Right. So that's. So this is a pre-Hilbert space structure. I mean, if you work with complex forms, you can permission, but I mean, this is a pre-Hilbert space structure. And you can complete it, of course, you get L2 of omega P of M or something. This is not a maximal, this is not a very good notation, but anyhow, so this is L2 integrable P forms. It's a completion of this pre-Hilbert space with respect to that. So we get that. Okay, so now the defining relation for this Hodge star then tells us the following thing is true, right? So finally we have that star omega eta is equal to integral omega wedge eta over d volume over n. Right? So this is what, so the point-wise formula we just do and then integrate that result. So basically, because this is integration of, you know, so should I go through the idea of proof, but you can see what's going on?
Should there be a volume form?
Oh, there shouldn't be volume form, no. Sorry. This is already an M form, exactly. Okay, so that's all nice. Now, one of the things that this whole machinery does for us is that it kind of, again, defines for us an explicit formula for the adjoint of the Courant D, right? So here's the definition.
I'm sorry, why did we need to conflict?
Well, later on, of course, we'll use, right? I mean, we completely, we took L2 or even sort of a space of sections, right?
Right, but for this we don't.
No. For this, actually, we don't need it at all. Yeah, exactly. Great. So the definition is that let the star be equal to. So there is some coefficient that I never remember. This is np plus n plus 1 star d star. So this is the recipe, the proposal for the adjoint of D. And so remember, this star now goes from where to where? This goes from omega p to omega p minus 1. Okay, so this goes from p to omega p minus 1, and that's this p that appears over there, so it goes to omega p minus 1. And the claim is that this is actually the adjoint of D. So lemma is that indeed the star of omega and eta is equal to omega. So let me put it like this: d omega eta is equal to omega and the star of eta. So this is for all omega belonging to omega p, for all eta belonging to omega p plus 1. Now, this is not the correct way of writing it because I use curly bracket for inner products, right? For the Hilbertian inner product. So I better write like this. These are really equality of numbers now. Because the way I wrote it before, this was on the level of forms, and that's not true. Because you have to, okay. So the proof is kind of interesting, but you know the proof. I mean, I just give you the hint for the proof, and it's very standard, of course. So the proof is you just use the Stokes formula. Let me write it. Proof by Stokes formula. So again, as I said, you can either assume M is compact, has no boundary, or if it is not compact, still has no boundary, but it's not compact, then you work with compact support forms, and then you're okay. So if you apply Stokes, you can write down an equation like this: 0 is equal to integral d star omega wedge eta. Okay. So this is an exact form. You integrate over the whole manifold, and it's going to be 0. I mean, because there are no boundaries. Because Stokes says that this, d is equal to integral of this form over the boundary, but there's no boundary, so this is 0. So 0 is equal to. Now, in terms of my choices, is that consistent with my choice over there or not? star, I'm assuming omega, maybe I have to, so where is this now? Omega is in, so this is p minus 1 form, right? And that is eta is p plus 1 form. Oh, wait a minute, that's not quite correct. No, that's correct. Sorry. So let's assume, so omega belongs to, so this belongs to n minus p, right? Eta belongs to p plus 1. So this is not quite correct. I have to assume that, say here, omega belongs to omega p minus 1, right? And then star of omega belongs to omega n minus p plus 1. And eta, I should assume eta belongs to, what is it?
You just need to switch the star onto it.
Maybe I'll put the star here.
Yeah,
Huh?
that's it.
Okay, so very good. Yes, that solves my problem and my further thinking. Good. I think that's. And then you expand this. This is equal to integral d omega wedge star eta plus. So there is minus 1, the degree of omega plus 1 integral omega wedge d star omega, and they use this formula. So formula A plus A. So you have to continue. Eventually, you get to what you want. That's straightforward. So I better not, because I don't have complete notes, but this is a standard. So. Okay. So this is the adjoint of D, the duality. Remember in the proof of this Hodge decomposition for even for elliptic complexes, I said there exists a dual operator, adjoint operator like P and P star, but I didn't give you the form of that P star. I said that P star we know is a differential operator, but explicitly we don't know, we didn't know much more about that. In each specific case, you can go on and work out the exact form of this P star, which in this case is this. Any questions?
For the general thing, there you would need to complete and you would define it as the adjoint in the completion, right?
Okay, so yeah, if you want to. So on the level of smooth forms, this is true. This statement is true and makes sense, and that's what it means. So I would say this is the formal adjoint.
Yeah, yes, no, what I'm saying. You would.
Yeah, no. There is a delicate issue there. Because if you complete, then this doesn't go to. It's not a bounded operator from L2 to L2. It's a bounded operator from L2 to some other Sobolev space, and so the return is going to be in the other direction. But we don't need that. That issue is completed. Okay. Okay, so that's good. Okay, so this is the adjoint. Now, what you wanted to do? Okay, so there is a formula also for Laplacian, which I use, but let me just tell you this. Also recall Laplacian for this, for the Ron complex, of course, this is just D plus D star squared equal to D star plus D star D. You see, D squared equal to 0, of course, implies that D star squared is also equal to 0. This star is star D star, right? And because the star squared is plus minus 1, so it drops, and then you get this squared equal to 0, gives you the star squared equal to 0. So this sort of thing gives you this. So we have that Laplacian, of course, and okay, so now what we want to do, we want to check this statement of, okay, before doing that, okay, yes. Here is another interesting lemma. Yeah. This lemma is the following, is that the operator Laplacian commutes with the star. So this is very important. Star delta is equal to delta star. I mean, this is explicitly given in terms of D and this D and star and D again, and so you can just go on and check that. This level is very, very straightforward. So that's okay. But now this is what we wanted to do first. So okay, because a star commutes with Laplacian, it means that it sends kernel of Laplacian to kernel of Laplacian. So a consequence of this commutation, of the symmetry of Laplacian, is that corollary star sends kernel of Laplacian on P forms, for example, to kernel of Laplacian on P minus 1 forms, N minus P forms. And in fact, this is an isomorphism. This map is an isomorphism. I mean, why is it an isomorphism? Because we know that star squared is equal to plus minus 1. Since star squared is equal to plus minus 1. So it's invertible no matter what. Okay, but by this result about Hodge, Hodge theory tells us that this kernel is exactly a space of, is isomorphic, cannot be isomorphic to a space of de Rham P cohomology groups. So let me write it, but Hodge theory, or Hodge decomposition, so maybe I just say by Hodge decomposition, or by the Hodge decomposition. We know that HP de Rham of M is isomorphic to kernel of this map, which is so these are harmonic P forms, right? Okay, so that's very nice now. So this shows that the peak Betty number is equal to N minus peak Betty number. Okay, so eventually we prove this result that for any closed manifold oriented manifold M, BP is equal to B and minus P. So this BP is dimension of HP de Rham. Notice that I'm not assuming any Riemannian metric here, right? So the idea is to put a Riemannian metric here, and you use this Hodge result, and then you get something which is completely topological. And of course, this is Poincare duality. But Poincare duality, in fact, is a bit more. So let me tell you, it's not that these two numbers are equal. This is not Poincare duality. The fact that the peak Betty number is N minus peak Betty number is not Poincare duality. It's Poincare duality is something much more canonical and even more interesting. It says that there exists a certain pairing, intersection pairing is non-degenerate. And that also follows from this. In fact, more is true. In fact, we have already proved this more. In fact, we proved more. So this, if you want this Poincare duality now, it says that this intersection pairing from HP Durand plus tensor H and minus P Durand of M R, which sends omega and eta integral of omega beta eta. This is a non-degenerate pairing. That's what is non-degenerate. So if you think about it, go through this isomorphism with harmonic forms, you notice that he did prove this much more interesting statement, that this intersection pairing. So the intersection pairing. So on is non-degenerate. Okay, so indeed, Poincare duality follows from this Hodge composition. Finiteness of the Durand cohomology groups also be proved, or general, even elliptic complexes be proved. Okay, that's good. So now I wanted to look at some examples, so that some of these statements in the specific examples don't need this much analysis, actually. They can be proved using simple ideas. So I'm going to check that. So, home group, any questions from home? Nathan, everything is crystal clear?
No, but it's getting there.
That's good. Any questions, comments? Jeremy? Okay, so let's look at some examples of this, so we can just look at these examples now. One nice example is to look at the case of tori. So here is example m equal to Rn. Zn, so n torus. So to check this, these statements that we made, we can put a metric on the n torus. And what is the best metric you can think of on the n torus? What's the best metric you can think of n torus? Sorry?
Flat metric from Rn.
Flat metric? Is that the best metric you can choose? Yeah, I mean, flat metric is the easiest metric, and yeah, I mean, that's really working with that is quite straightforward in most cases. So I put plus flat metric. So you have the flat metric on Rn, and you take the quotient map, you induce a metric on the quotient. So, you know, this is a very nice metric. So in this metric, you can work like you are on Rn, except that you're working with periodic functions. Otherwise, everything is up. Anyhow, so what is omega p of m? So this is equal to C infinity of m. Tensor HP of V. So this V, you can I mean, imagine V is it really doesn't matter much here, but let's say V is Rn star. So this is like tangent space, cotangent space to this guy, to M. So this guy, so of course, I mean, this is the case because the manifold is parallelizable. Right? So the manifold is parallelizable, and every P form, you can write it as sigma Fi1 with IP dx I1 which dx IP, right? In increasing order, these guys. This is Fi1. So what is wedge? I mean, this is awful. I1 IP. Fi1 IP belongs to C infinity of n. So it's just a periodic function, right? So we've got just we just have this periodic functions. Okay, so we have a good grasp of P forms on this manifold. It's very straightforward. And what about this Laplacian? So if you look at Laplacian, so Laplacian is really like this. It's equal to identity tensor. So Laplacian on P forms on functions, zero forms. For this guy, also maybe the other way around, I should say, is delta zero tensor identity. So this delta zero is Laplacian on P forms, which is, it is Laplacian on functions, which is minus sum di squared I from 1 to n, and this di is ddxi. So you have to check this. I mean, you just write down equation for d star, and then you do that, and then there is this minus sign. This very important minus sign comes out. All this. So you have to check that. Right? So you can check that. So now, what are harmonic P forms in this case? Is equal to what? So if you have such a form and you want it to be killed by your P Laplacian, then each of these coefficients has to be zero. So, right? So delta sigma. So each of these coefficients have to be zero, but these coefficients, have to be in the kernel of the Laplacian. So but these are smooth periodic functions. This means that these guys have to be constant. That's all. Equal to constant. Okay, so in other words, the kernel of these P forms is nothing. The kernel of this P Laplacian is nothing but P forms with constant coefficients. Right? Okay, so we put P forms the constant coefficients. Okay, so in other words, this kernel of is really isomorphic to this guy itself. So it's just HP of Rn star. Right? So in particular, its dimension is n choose P. Dimension of I mean, we have even a kind of canonical basis for this space. So dimensional kernel of delta P is equal to n choose P, and the basis is given by these guys, dxi1, dxi. So of course, this is going to be equal to dimension of the P by this result, Hodge theory, P duram of Rn mod Zn, right? Okay. But so this is now by Hodge theory. But in this case, I'm saying you don't need that because there is an independent calculation that you can guarantees you that in fact this dimension is n choose P, and that's Kunet formula. Okay, but this, by this I mean, can also be obtained by Kunet formula because I mean this manifold is a Cartesian product of n circles, so you can apply Kunet formula and then you get that. So in this case, it's a statement of Hodge theory. In this case, is a consequence of Kunet formula, so it's a topological statement. So this is good to check because you know, proving something general is good, but then we have to check something. There is a case. Any question about this? Okay, maybe in this case I will. Yeah. So my claim is that this Hodge decomposition for compact Lie groups can also be obtained from much more elementary results, but maybe that will take a little bit of explanation. So maybe I will postpone this to another time when we give again examples. So anyhow, so that's. Oh yeah. So let me give another example. Okay. So this was our first example. We checked this statement about Hodge decomposition. Oh, by the way, we didn't check a statement of Hodge decomposition. We just checked this statement that harmonic P-forms, dimension harmonic P-forms, dimension of P cohomology. What happens to Hodge decomposition itself? That also should follow from this baby Hodge decomposition that I did, because all you have to do, you have to work on this, on the level of this Rn's, I believe. Yeah, I don't know what to do with the Hodge decomposition in this case. That's an interesting little exercise actually to do. Okay, so I just put it as a question. Yeah. So that's not. Okay, so anyhow, so here is another example, but this example is kind of related, but I don't know exactly how. So this is Helmholtz decomposition. So this is what we did last time. So let me write it. Helmholtz decomposition. So sometimes this is called the, I mean, is the most fundamental result about vector fields in R3. So, so let F equal to F1, F2, F3 be a vector field in R3. So this is a very general vector field in R3, field of vectors, with enough decay, rapid enough decay at infinity. You don't need the rapid decay. You just need some decay at infinity. I mean, it should be of some order. I'm not sure exactly what, but it's not too rapid. It's just like 1 over maybe distance squared or something like that. It's not too much. I can drive it, but I don't need it. With some decay, I won't tell you exactly how much decay, but anyway, with decay at infinity.
Why won't just compact support work?
Sorry?
Why won't just compact support work? Just assuming that your compact is
Of course, compact support also works. No, but I mean, I want to give a result which is more general. Of course, compact support also works. With decay at infinity. For example, compact support. So that'd be like e.g. compact support. But that's very drastic. I mean,
sure.
e.g. compact support is enough. Okay, so then the result says that you can write F uniquely as sum of two vector fields. Then there exist unique vector fields A and B on R3 such that, first of all, A is curve-free. So there are no vortices in A. And B is divergence-free. Oh, that. So this B is not, the flow of B is not expanding or shrinking. It's just volume preserving. And this one has no rotations in it. So, and of course, F is equal to A plus. So you're supposed to see some similarity between this and Hodge decomposition, but there are some subtleties, right? Some issues here. I mean, you have to identify those which are curved as those which are in the image of D, for example, or image of D star. I don't know yet. And those which are divergence-free as image of the other one.
No, but this.
And then there is another term which is missing. Another term which is missing. These are harmonic, whatever, harmonic forms, for example, harmonic bond forms or two forms or something. That's also missing. So you have to account for those facts. Otherwise, but there is some similarity. You can see that. So this was proved by Helmholtz around 1860. So this is way before Hodge. So you may try actually. It's a good exercise. A good exercise is to try to prove this using Hodge decomposition. So I give you this as an exercise actually. So exercise is this first of all. Can you derive this? From Hodge decomposition? I don't want general blah blah. I want you to prove it really. I mean, no philosophy. So this is the question. Of course, Hodge decomposition was for compact manifolds. It was very essential. This is not compact. That's one thing you have to be careful. You may think, okay, I can just compactify R3 to three-dimensional sphere and work with that. But then you have to give me all the details. I mean, to give yourself, in order to make sure that you really understand what's going on. because I can prove it totally independently using some basic PDE results. I mean, some green function technology, I can prove it. But there is some resemblance to Hodge decomposition, and in fact, is kind of quite related. But the point of the exercise is to make sure that you can really derive it, not just there is a relation, vague relationship, to derive it. And to do that, by the way, so maybe this would be very helpful, actually, because this kind of comparison is helpful. You may use, so what you may use? You see, we have a map from C infinity of R3, right? By gradient, applying nabla, we go to vector fields on R3, right? And from vector fields, we can go to vector fields again by applying what? For example, by applying curve. Yeah, that's good. Yeah, applying curve to vector fields. And okay, and then I can go from vector fields to functions, C infinity of R3, by applying the divergence operator. So here is divergence. So this is divergence. This is curve. And of course, this is gradient. First of all, do we agree that we have a complex here? I mean, curl of gradient is 0. I have to teach these things to my calculus class in a month or so. So I better prepare for it. So curl of gradient is 0. I believe divergence of curl is also 0. And so I can go to 0 here. These are totally, I mean, at the end I put zeros, that's not, this is a complex. Good. Now, I want to compare this complex with the Rho complex of R3. So I get here again omega 0 of R3, which is exactly the same thing, right? And now I have D. So D, I go to omega 1 of R3, right? Now here I have to write an isomorphism between vector fields on R3 and bond forms on R3. So what is this isomorphism? Well, I mean, this isomorphism, say, I don't know, so this isomorphism would be like this. So F1, so let me put it like this, F1, F2, F3. I can just, because I want the diagram commute, I can just send it to F1 dx1 plus F2 dx2 plus F3 dx3. So if I use this isomorphism, here is, so let me use that. Yeah, so this is alpha 0, this is alpha 1. Alpha 1 is this map, this isomorphism. Then this diagram I make sure it commutes. So that's now, what about this one? Well, I mean, we have this D, and then we go to omega 2 of R3. Now, here, this isomorphism alpha 2, it's a bit more tricky, right? So first of all, what is omega 2 of R3? Yeah, we can write it as A1, say AX, I mean, I don't know, let me put it like A1 dx wedge dy, right? Plus A2, this is a bad notation, I'm afraid, dx wedge dz plus A3, dx I use, and then dy by hdz, right? So what would be a good notation? Well, whatever. Now, I want to have an isomorphism of alpha 2. Of course, this vector field again has 3 components. So, of course, 3 components and 3 components. So you see that this matches, but you have to write it with the right signs and right order. So, do you remember, or do you know what alpha 2 should be? No, it won't. No. I mean, alpha 2 of f1, f2, f3 to be f1 dx dy. This won't work. That's too simple. You have to match signs and change orders. You have to work it out. You can do that. You can work this out. And now, what about this one? Again, there is d here, and there is c. There is omega 3 of R3. And last one, there is this isomorphism alpha 3. Now, this omega 3 of R3 of course, I mean, I have to write it like this, right? So this is also, I mean, this is just functions. This is f dx h dy h dz. So most probably this map alpha 3 is going to be a function f to f dx dy dz to this 3, 4, but maybe plus minus sign, but not plus minus 2. I mean, it should be either plus or minus. So this alpha 3. So alpha 3, I'm going to guess that alpha 3 of f is going to be equal to f dx h dy h dz, but maybe with minus. I don't know which one. So the point of exercise is to check that. Okay, so that's nice. Now, but that's not all. You have to work out the star now. Also work out the star. But if you check this, at least something should be clear. Namely, cohomology of this chain complex is going to be cohomology of that chain complex up there. And but we know the cohomology of this chain complex. This is trivial except in dimension 0. This is by Poincare lemma. This complex is acyclic except in dimension 0. So it follows that this upper complex is also acyclic. So that's why we tell the students that if divergence of the vector field is 0, then that vector field is going to be curl of another vector field. Or if curl of a vector field is 0, that's going to be gradient of another vector. So this first one are conservative vector fields. The other ones are divergence or irrotational vector fields. So we have this terminology, which is kind of dual to the other terminology, because for the other two terminology we used irrotational and divergence free. But irrotational and conservative are the same, we're saying. And divergence free, well, we didn't use another different notation, but just for both cases, just use divergence. So anyhow, this is kind of, I mean, it's a little exercise, but it's kind of fun to do it. Just draw formulas for the star and interpretation in terms of vector. Any questions? No? So, okay, that's good. Now, these are the examples. Now, I want to.
I just have one thing. Is this really a manifestation that's kernel direct sum image. So that's why the Hodge.
Which one? I mean, the one that I wrote.
Second vector field. That second
This one? No, this has nothing to do with Hodge decomposition.
No, I mean Helmholtz decomposition.
Helmholtz decomposition.
Helmholtz decomposition. So I was just thinking like the second term.
Yeah.
Vector fields on R3.
Mm-hmm.
If we can, so that will be if we can like somehow identify curl with D up to whatever sign that you said, then like it will make this would just translate to kernel D image.
It's not kernel D. Image of D,
sorry.
direct sum image of
Kernel
the
D
star.
D star.
Not kernel of the star.
Yeah, sorry.
No, it's image.
Yeah. So the harmonic part is not. So the whole thing should have been harmonic, direct sum image, direct sum.
The harmonic part is 0 in this case, is missing. And the question is why the harmonic part is missing. That was the part of exercise. The harmonic part is not there, but the other two parts, which is curl equal to 0, or the image of the curl and the image of the divergence operators. Those two, the kernel of this operator and the kernel of the other one. Well, you see, if you think about it the other way around, the kernel of this, curl operator is the image of divergence operator and things like that. So it's the image of gradient operator, sorry. So it's written in terms of kernels, but you can also cast it in terms of images. And that would be the connection to Hodge decomposition. Yeah, I mean, because there are different operators. There are these two operators, and there are duals of these things. But the duals are expressible in terms of the same operators again, up to some sign or something. Yeah, because this isomorphism, especially in the middle, is not trivial. I mean, there's a sign change in somewhere. I mean, so I highly recommend you work this out for yourself. That's all. Okay, so well, I mean, people say Hodge decomposition is really kind of Helmholtz decomposition in this case, but okay, but there is some subtlety. I mean, some small points, maybe not subtlety, that you have to be aware of. Okay, good. So, I mean, in case of Lie algebra, I'll do later on. That's okay. So, can I erase this then? Okay. So now we can actually start some new section, which is spectral decomposition of L2 of E. Okay, so this is new stuff. So this is now spectral decomposition. Okay, so now let's assume that E over M, let it be a Hermitian vector bundle. A Hermitian vector bundle over this M, which is a closed oriented Riemannian manifold, over M, which is a closed oriented Riemannian. Okay, that's a thing. So we have this Hilbert space, and let okay. So before that, let P from C infinity of E to C infinity of E. Let's assume that this is a positive self-adjoint, be a positive. I mean, if I say positive, it means it's already self-adjoint, but I mean, like, I would say formally self-adjoint, at least. Self-adjoint pseudo-differential operator of order, of some positive order. It doesn't have to be an integer, of some positive order, D. Okay, so this is a general setting. You can think of like first order operator, second order operator, but it doesn't have to be integral order. This is simple differential order, but it's positive. Okay, now, so then for any lambda belonging to R, of course, this P minus lambda is also, and elliptic. So I should say positive self-adjoint elliptic. So this is important. Sorry. Elliptic pseudo of order D positive. Then for any lambda bigger than any lambda in R, this operator P minus lambda is also elliptic. P minus lambda is elliptic. Well, I mean, the reason, of course, for that is that you're just changing the zero order part. You're not changing the top part or middle part. So the ellipticity doesn't affect the ellipticity of the operator. So this is also elliptic. So by finite Delta result, I know that the kernel of this guy is finite dimensional. So E lambda, which is by definition is equal to kernel of P minus lambda. Now I look at P minus lambda going from C infinity of E to C infinity of E. So let's look at it like that. This guy is finite dimensional. Finite dimensional for any lambda in R. So this E lambda, of course, is the eigenspace of this. And if, so first of all, we know that these are finite dimensional. And if dimension of this E lambda is positive, then this lambda is an eigenvalue of this operator. Eigenvalue, and that's an eigenspace of this eigenvalue. Right? So, I mean, the idea, the fact that this guy is self-adjoint, or formally self-adjoint, it doesn't matter. And this self-adjoint implies that these spaces are orthogonal to each other. E lambda and E mu are orthogonal to each other if lambda is different from mu. Right? First of all, if lambda is different from mu, that's one thing. And second thing is that, of course, lambda, I mean, if E lambda wants to be non-trivial, lambda has to be non-zero because, I mean, it has to be non-negative, right? Of course, this implies that lambda is bigger than or equal to 0. Over negative one, there can't be any kernel. This also follows from positivity. So positivity. One implies that dimension implies that. Okay. So now what do we have? We have then this Hilbert space, which we know is a separable Hilbert space, L2 of E. L2 of E is separable. I mean, we are in the separable case in this case. You immediately conclude that there's just going to be a countable set of eigenvalues, right? That's, I mean, because, I mean, this orthogonality and Hilbert dimension implies that there exists a countable set of eigenvalues. But now what we want to prove is two things. The first one is that actually these E lambdas give us a complete orthogonal decomposition of L2 of E. So what we want to prove is, there are two things we want to prove. We want to prove the first one is a completeness statement. So this completeness is the following, that L2 of E is equal to direct sum of E lambdas, closure. So there exists a complete set, I mean, orthonormal set of Eigen Functions, essentially. That's what it's saying. Right? So that's one thing. But still, you may guess, or you may think that, okay, that's possible, but then all these lambdas are kind of confined in some interval, for example, 0, 1. Could be countable, many, infinite countability of them. And but we want to show that the second part is that if we order lambdas by, say, you can always order it like that, right? Lambda 1 less than equal to lambda 2 less than equal to lambda 3, etc. Then we want to show that they go to infinity. So this we want to show. And in fact, we want to show much more. We want to show that it goes to infinity at some fast pace, rather fast pace. And in fact, I want to show that this lambda n is kind of asymptotically it grows like n to the power d, okay. What I want to say in this case, like n to the power d over the dimension of the line. So this m is the dimension of the line. Yeah, I believe so. So there's a, so as n goes, so lambda n, as n goes to infinity. So there is a growth condition on these things that's very, very important. We have to prove this eventually. But maybe I think the proof will go like this. We will prove a bigger statement, and then after some work, we will prove something like this. So I'm going to fix this, the exact thing. This is asymptotic equality. The ratio goes to 1. Of course, I have to put still some constant here, which I'm kind of very vague here, sorry. I will fix that so once I get into something. So these two things now are not obvious, right? First one is this completeness. It's not obvious at all. I mean, we have found some space of eigenfunctions which form an orthonormal set, but why it's complete? And the second one is this growth. It's growing fast. So this is Boyle's law, of course. On asymptotic growth of eigenvalues. So we want to prove this on the way. So, okay. Any question? Yes.
Why do we know that L2 of E is separable?
How do we know that L2 of E is separable? Yes. So to start it, we have to assume that our manifold is second countable, I guess. So that's what we know. And you know, I mean, then C of n, continuous functions, for example, of n, has some a countable dense set. If your manifold is has a countable basis in its topology, then continuous functions on that as a countable dense set. That makes sense. And continuous functions is dense inside L2 functions. So then what we know is that this Hilbert space has a countable dense subset. So its Hilbert dimension is countable. So it's essentially separate. It's separate. Yeah. So to get into non-separable things, in this case, you have to go into some strange manifolds. Yeah, we are not working with it. All right. So, okay. Any questions or comments? But again, now let's look at some examples and see these things in practice, how it's done, and then I will give a proof of at least one. A proof of two, I'm not sure I can give today, but next time. Okay, so now, again, it's very important to look at examples. So this is example one. So this time let M equal to Rn mod lambda. So lambda inside Rn. So this is a lattice. So lattice, by definition, is the set of the form ZE1 plus ZE2 plus ZEn, where E1, 2, En is just a basis for Rn. Any basis. Of course, you can have many other definitions of lattice, but let's look at this definition. It's the set of all elements of Rn, which is of the form. So this is, of course, a subgroup of Rn. In fact, it's free abelian group, right? So lambda is a subgroup isomorphic to Zn. It is a free abelian group of rank n. But the structure of these vectors, E1, E2, En, the way they sit in Rn is very, very important. And classifying lattices as a result is a very difficult problem in general. So you have this E1, for example, and E2, and then you build everything based on these things. E1, E2. Okay, so, and you go on. So, but notice that these elements E1, En is not unique. You can choose a different basis for the lattice. Okay. So that's the lattice, and then so this is essentially topologically is a torus. So plus flat metric. Now the Laplacian. So we just take E to be the trivial line bundle over this. I mean, if you want, you can take trivial line bundle. So L2 of then E is just L2 of M. Okay, with respect to this, yeah, I guess maybe the Lake measure, I guess, or well, let me just write L2. So just okay, and then Laplacian P is equal to delta is Laplacian, which is minus some di squared. This is the Laplacian. Now, so now we have to identify the Eigen functions for the Laplacian. So we have to solve this equation delta f equal to lambda f. So first of all, let me give you some solutions, and then we'll argue that these are everything. So let f of x be equal to exponential of 2 pi I x. So then it will be like x and gamma. So what is gamma? So what is gamma? So where gamma belongs to the dual lattice, lambda star, or any gamma belongs to this. So what is this dual lattice? The dual lattice I define to be the set of all, say, y belonging to Rn, such that the inner product of y and x belongs to a z for any x in your lattice. Along your lattice lambda. Okay? So, so it is a lattice. Well, I mean, it's a subset that has this property that if you pair it with any element from the original lattice, you get an integer. Okay, so this could be a bit confusing at first, but imagine, for example, you have lambda equal to maybe like 2e1. Okay, so let me write it like this: z times e1 plus z times e2 in R2, where e1 is this vector 2, 0, and e2 is the vector 1, 0, 3, just to make life easy for myself. So it's twice the unit vector in this direction and 3 times that. So of course now this I can argue that then this lambda star is going to be equal to lambda z times half of e1 dx sum z times 1/3 of e2. This is, we can prove. It's not difficult. But here is a nice exercise. The exercise is to show that this is actually again a lattice. And in general, understanding the shape of lambda star from shape of lambda, figuring out it's not so easy, except in this simple case where it's a rectangular lattice or orthogonal lattices. But for this kind of slanted, slopey kind of lattices, guessing the shape of lambda star needs a little bit of work. But so let me write down the exercise then, and then. So exercise this is a lattice. In other words, you have to show that there is a basis such that this can be written as ZE1. Okay, my coffee is over, but then luckily time is also. Yes.
Isn't the dual lattice spanned by the vectors half, 0, and 0, 1/3?
Sorry.
What we have now is that the dual lattice is spanned by the unit vectors. Which should be like half, 0, and 0, 1/3.
Oh. Well, no. I mean, E1 is 2, 0.
Yeah, so half E1 is 1, 0.
Half of E1. Yeah, it's 1, 0, yes.
But doesn't 1/2, 0 also, like 1/2, 0 also dot products to integers with that one?
But this is in the lattice again, isn't it? It's
Yeah, so I think, oh, the dual lattice would be, one of the vectors in the dual lattice would be 1/2, 0.
so this is E1, like twice I, and this is E2, which is 3 times J, right?
Okay.
So I'm saying that the dual lattice better be half of this,
Half of I, right?
half of this, and I mean, certainly I have to take 1/3 of this because I want to, oh, you're saying, yeah, 1/3 of this.
It shouldn't be 1/3 of E2, it should be 1/3 of the unit vector in E2.
Oh, did I say E2?
Yeah, okay, I think we mean the same thing. Because you say it's spanned by 1/2 E1 and 1/3 E2. But E1 is the vector 2, 0.
E1 is the vector, no, E1 is, for me, E1 is the vector 0, I mean 1, sorry, 2, 0, yes. But for me, E2 is the vector 0, 3. Yeah, E2.
So you say that the dual lattice is spanned by the vectors 1, 0 and 0, 1.
Yes.
So I think it should be 1/2, 0 and 0, 1/3.
Oh.
Because 1/2, 0 in a product with any integer times 2, 0 will give you an integer.
Yeah, I'm making an obvious mistake here, I guess. But sorry, maybe my notation is not ideal.
I think the confusion is between E1 and the unit vector in direction x or y.
Yeah. No, E1, I mean this one.
Yeah. So I think the dual lattice should be a quarter E1 and 1
Quarter of E1?
Yeah.
Oh, why quarter?
Because you want it to be 1/2, 0.
Do you think it should be half of the unit vector in E1 direction?
Yeah.
I can't get you. I'm just maybe my brain now. Okay, I trust you guys are right, but I will. So okay, so this is has to be decided yet. Okay. All right, so now, so lambda is a lattice. You do this exercise. I think I'm missing something here, very obvious, but that's okay. Anyhow, so now let's write this f. So definition. So let f of x. Well, I just wrote it equal to so e to the 2 pi I. X gamma. So now for every gamma belonging to the dual lattice, lambda star, this f of x is gamma periodic, right? Is gamma periodic. So this gives us a function on the torus, right? I.e. of x belongs to C infinity of Rm on lambda. So this is that. Okay, but it's not just that, it's actually an eigenfunction for Laplacian also. And if you want to compute this guy, delta of f, you notice that essentially what you're doing, you just multiply by 2 pi I, and then again multiply by 2 pi I, and you get the norm of this gamma square. So what you get is that you get 4 pi squared, norm of gamma squared, same function, f. Okay. So this calculation is easy. So we have produced lots of elements which are in the kernel of Laplacian minus lambda or Eigen functions. Okay, so let me write it like this then. So for each n, we can, I mean, for each, say, k bigger than or equal to 0, let ek be the set of all points in the lattice, dual lattice, I mean, gamma belonging to gamma star, such that 4 pi squared, length squared of gamma is equal to k. Okay. So this EKs, I mean, is an eigenspace for, so EK, so what I'm saying is that it's not the set of all gamma such that, I mean, so I want to take these, okay, so now, no, I don't want that. Okay, no, that's okay. So then, so this kind of conflicts with my earlier notation. I don't want to be in conflict with my earlier notation. What I'm going to say is that this then for belonging to k. So I'm going to revise this actually. Ek be the set of all functions e to the 2 pi I inner product x and gamma for those gammas such that this equation is satisfied. Okay. So then basically Fourier analysis shows Fourier theory implies that these guys actually are orthonormal, form an orthonormal basis for L2 of M. That is set of all, so maybe for orthogonal basis for L2 of M. So in other words, L2 of M is equal to direct sum of these EKs, where K is a square length of any lattice elements. I mean, okay, so to be, and this is, so there is no other solution And this is exactly the statement of completeness. In other words, this. So what I'm saying is that completeness in this case is just a consequence of Fourier theory. So Fourier theory implies this implies completeness. And also the fact that these eigenvalues are going to infinity, it's clear because in a lattice, the dual lattice also in the lattice, you can just pick larger and larger points and they're farther and farther away from zero. And actually you can guess how fast they are growing. You have an idea how fast they are growing, in what speed. Roughly you can guess how fast they are. So that's so this statement follows from Fourier theory. So there is another case that the general statement follows. Again, it is a group theory case, but that's for compact Lie groups. So I think in that case, the Peter-Boyle theorem gives you an orthonormal basis for L2 of G. Right? And I'm going to argue that this actually implies this completeness. I'm not 100% sure about that, but I think that's what's. So this lives in that. Maybe it was not a good idea to do this general case. Maybe I should have just worked on the case of circle. So that would be much better. Just starting with the circle. Okay, so this I do next time. Let's go back to the special case. More modest case of circle, you can see things much better compared to this version. Okay, I think we can finish now. Any questions or comments? So we can actually stop the recording.